Alright, so I worked out how to do calculus with this notation. So I noted a few other components that I have used in the past. So there's the number-based notation, this slash here. So this is just a suffix that's followed by an indication of what the previous expression's number base is. And this is convenient shorthand for things like quadratics, like this, ABC. With respect to x is 0, but you can also be used to indicate any positional value from reals to p-adics in any base. So 210 in base 3 is 21, positive 21. Infinitely repeating 6's to the left, ending in a 5 in base 7 is p-adic negative 2. And then there's the norm or the cast notation, the vertical bar. So this is the abbreviated form of absolute values, because when you take the absolute value of something, you're casting it from a vector to a magnitude. So you're no longer able to do things like add, subtract with that value. So there's really no point in surrounding it, because you can't do anything with it at that point. It needs to be cast something else after you do that to it. So use this as a suffix. And this allows us to find absolute values or recast vectors from one unit to another. So this previous example, right, 210 with respect to 3 in base 3 is positive 21, but if we take the norm of that, it's just 21. Or if we take the norm of 210 in base 3, so that's not the norm of 210. I don't know how to say this differently. Anyway, that's the p-adic norm. That's the p-adic absolute value, 1 and 1/21. We can use it to cast from one type of unit to another. That's really what it's doing all along. So here we're going 1 foot to inches, so it becomes 12 inches. Here we're taking positives to negatives, so we go positive 13 converted to negative 13. Or we can do this as like this batch function, where we handle a distance and a time, and we manage that. So the distance is the numerator, the time is the denominator, and we're also converting 6 kilometers to meters and 1 minute to seconds, and that ends up being 100 meters per second. And we can do things like complex numbers, and so the norm of this complex number is just 1, right? And using this notation, we can also get classic p-adic absolute values very simply. So the leading values, we don't care, but there needs to be a repeating sequence of zeros to the right for k places. That absolute value with respect to base p will be 1 over p to the k. That's what that means. Alright, now the more interesting ones. So those I've shown before. The more interesting ones is these are the essential calculus operations in the commutative batch notation. Right? So we can do integrals. So here our reference frame is established by the function that we're integrating. And then what we're doing is we are taking the dependent variable, and we're multiplying that by the change in the independent variable. And you can actually see that directly from what happens here. So this linear function becomes a quadratic because we're multiplying it by x. Right? So the linear function of x becomes a quadratic function of x, and the whole function is literally multiplied by the steps in x scaled by the corresponding y. Okay, and then we can take a definite integral too. I used a little bit of shorthand here, so this is the same. This is the same thing here, right? We're just using the same thing, but I'm assigning that to capital A, and then what we're going to do is we're going to set our reference frame to P, whatever that might be. This is going to be our upper limit, and then we're going to look at this result with respect to that reference frame, and then we're going to subtract from that result the same sort of thing with our lower limit. So you get this. This is just how definite integrals are done. Nothing fancy about this, but the fact that you can just do it very easily with this notation, and it's written just linearly in plain text. There's no like fancy scripts or anything that's required for this. It's kind of nice. It's kind of nice, and it's the same exact notation that gives us all of the other operations, from addition to I'll flesh this out a little bit more: logarithms, tetration, multiplication, division, summation, so addition, subtraction, incrementation, decrementation, existentiation. All of that can also just give us integrals too, and derivatives. So this is very similar. So our reference frame is established by the function that we're working with, but then what we're going to be doing is we're going to be taking the change in the dependent variable divided by the change in the change in the dependent variable divided by the change in the independent variable. I don't know what I started saying, but now I know what I did say. Okay. So you can see this here. This is a quadratic going to a linear, so we're dividing by x. That's literally there. And this reflects standard notation, right? You get basically your function times dx when you're integrating. And when you're taking the derivative, you get your function dy dx. And that dy divided by dx, or d over dx. Okay. So notice here that the quadratic function of x becomes a linear function of x. The whole function is literally divided by the steps in x, scaled by the corresponding changes in y. And we can also take limits. So this one is really nice. I've pretty much been thinking about limits this way for a long time now. I think several years at this point. Well, in a sense, I've been thinking about them like this for a couple decades, but in a very strict sense, this is literally how I've been thinking of limits for the past few years. Yeah, so this is a more kind of normal way that you would write it, right? So you got the limit as x approaches 0 of something like 1 on x. Okay. Here, what we're looking at is we've got this function, but what our reference frame is, x is set to 0. That's what this means. And then we're moving away from it in either direction by the infinitesimal unit along x. Or because we're in the neighborhood of 0, we could set plus or minus the infinitesimal x as our reference frame with respect to this function. But if this was, say, like you're looking at the limit as x approaches 7 or something, then you wouldn't want to abbreviate it this way. You'd want to use this, and this would be like a 7 right there, or whatever your value is. Okay. So same sort of thing, except we can. So this is the general case, the general limit from both sides. This is from the positive side, and this is from the negative side. And literally the only thing that changes is the sign on the infinitesimal x term. Okay. So the output of the indefinite integral and the derivative are functions, because the reference frame is constantly changing, never held static, right? The reference frame is literally a function, so we get out a function. Under integration, the resultant function yields the shape constant for the input function because we're taking y dx. While under the derivative, the resultant function yields the slope of the input function because we're taking d on dx. The definite integral involves evaluation at the upper and lower limits of integration by way of setting the reference frame for the output function to those limits, and then summing them appropriately. So you take the evaluation at the upper limit and then subtract the evaluation of the lower limit. Limits themselves are found by just defining the reference frame and moving the infinitesimal unit in the desired direction. This requires the sign and dimension to be indicated at minimum. So it's not just the infinitesimal unit, it's positive infinitesimal unit along x, or whatever is appropriate. And there you go, that's the basic calculus operations. And when I started fiddling with this, I wasn't sure that I would get this to make sense. And still, like, I only did this a few hours ago, so there's still likely to be some weird glitches in this that I'm not seeing at this point. But I'm pretty confident that this is at least close to a final form of what this is going to look like. So now you have this single notation that treats kind of most of mathematics as non-commutative. I do want to look at things like matrix multiplication, see if I see what we can do there. But when we get non-commutativity, it's explicit the reason why. It's that we have reference frame changes. Right? So the reason this is very strictly laid out is because of the reference frame changes that are involved. And because that is explicit in this notation, it's never a mystery whether you're dealing with something that's commutative or not. It's just part of what's being expressed directly. So, yeah, there's that.